Yeah, so today we're talking about secure backend architecture for fintech and payment systems. So my name is Okoli Johnson. I'm a full stack software developer specialized in building scalable and durable backend architecture systems. I'm an MSc graduate of cybersecurity from University of Birmingham and a degree holder of computer engineering. And today we're talking about secure backend architecture for fintech and payment systems. So why this is very different is because it's a very unique niche in software ecosystem because it has to do with money and that's very sensitive. So it's different in the sense that money is stateful and irreversible. Most actions are equivalent to not being reversible because once you initiate, even though now there are more modernized technologies where you could actually retrieve transactions, but it's still based on timed activity and you can report transactions too. Then also errors tend to affect users instantly in real time, and this affects and makes trust fragile and very flexible in terms of opponents against the company's reputations. The fintech system is strictly governed by regulatory and expectations that are needed to be met. Then every decision has a financial sequential consequence in the sense that for every action, it's actually has its own consequence. For every architectural decision you make, it affects the system. Engineering responsibility in financial system. So when designing payment systems and wallets, their core features or terms to note in terms of you want the transaction to be consistent. You don't want inconsistent transactions. You want it to be deterministic. So from the transactions, you can actually figure out the states of action. You also want to be able to perform forensic activities on your financial or transaction data. What that means is you should be able to compile and assemble all events and make sense of it in forensic analysis, then maintain under failure conditions. All this warrants to the fact that money must be atomic. So it's either you perform the whole transaction or you don't perform it. So it has to be an atomic activity. Then the common failures in payment systems are double charges. That's when you actually do retries with no idempotency considered, or where you have balance sheets based on you updating the balance without fact checking with the ledger to be sure that the figures are accurate, or when you have we have what we call race conditions too, more like two different people trying to perform the same activity. At that point, there should be like a preference as to which should go and which should not go. And the feature used to also curb that would be you having a lock-in transaction, or you have a lock-in feature where you can lock that transaction, that particular entity for the time being and prevent subsequent concurrent actions on that particular transaction. Then it should also ensure that you have consistent transaction states. Where it needs to sync with an external provider, you should only commit it after you've gotten a valid response from that external provider. Then when you have poor audit system or poor audit trails, it tends to make your history not dependable and makes it messy and mutable. So the base architectural foundation in fintech payment system would be for you to maintain a ledger first design. So what that means, it should not trust balance directly. It should always depend. It should always trust the ledger because the ledger holds all the transactions and the state, whether it's a credit transaction or a debit transaction. You should always derive your balances from the ledger itself because that should remain your utmost source of truth when determining balances. Then what that means, you should only append. You should make your ledger immutable, and that way to do that would be to actually introduce where you have chained ledger. So what that means is if any of those ledger is missing, the algorithm or the matching feature will not be able to match because the H mark would fail. Then you should ensure double entry accounting model. So what that means is you have like the credits, and for every transaction there should be like a credit and debit transaction, and also a status to be able to keep track of the status if it's pending or completed or still in progress. Then derived balances, like we said earlier, you should be able to derive it from the ledger without having to depend on just the wallet balance directly. And every movement, every transactions are being recorded for audit purposes too as well. And it's more like a simple model where when you have a particular transaction coming on, you validate transaction based on the user's authentication, based on the required keys you need, probably the transaction ID, the reference. You validate all those regarding transaction, and you can authorize the transaction. So this is what the ledger looks like: a double ledger, double entry ledger. You have the debits, you have the credits. So this is more like a simple transfer. So user A is making a transfer to user B. So this is the events box that keeps track of the activities being done on the system. So for this particular one now, it's initiating a debit and a credit. So it's debits user account A of 100, and then it's credits that value to account B, which was previously 400, and ensure that all these activities are being logged, and also notifications where you notify user A, your account was debited, user B, your account was credited, and then fraud anomalies to detect scrupulous or unwanted transactions too. Then is an high-level fintech architecture where you have this is the client side. You have the device, either a mobile phone, from tablet, or from the laptop. You have that part from there. And then an API gateway that would serve as an interface between your backend services and the client side that helps to route the traffic from there. And then you have the other services, whether the auth services, the transaction service, the wallet service, and other services, and also the database for audit trails and payments providers. Then transaction integrity and state management. So this is more like a life cycle of a transaction where you validate the transaction, you mark the transaction as pending. So for instance, someone tries to top up the wallet. So the first thing you first do is you validate that all the data has been sent are actually correct and factual. Then by default, you pen that transaction as pending, and you lock other financial sources. For instance, someone is trying to make top up the wallet. You have to like lock other instances, more like the person's ledger or the person's related models, so as to prevent conflict or racing. Then you call the external provider, which in this case might be Stripe or might be Cloud Pay or whatever payment system you are using. And as soon as you get that response, you can now commit the transaction, and then you emit that event. And then when you emit the event, if it's the one that actually requires a callback, that means you have to still await the response from the provider, probably through webhook or other means, where you now update the transaction as completed after the whole cycle is done. So we talked about concurrency before. So this is an instance where you can actually experience concurrency when you have two different entities trying to make the same action. More like two concurrent withdrawals being made, and what that would impact is the account goes negative. So to curb that effect, that's where we talked about the locking, the optimistic locking too, transaction integrity check, and the potent key and distributed avoidance. So what that means is, if for instance two different entities are trying to access a particular transaction, you have to hold that transaction down for it to be completed, and then before you allow the other transaction. And then since you're having a potent key, if the keys are the same, you just have to neglect the next or the other transaction and prevent racing concurrency as well. Yeah, and then this is the idempotency part. So idempotency is just mentioning that a transaction is immutable and it's unique in the sense that it avoids duplicates and duplicate transactions. So because most of our times we do retries, we do webhook retries based on maybe the first transaction failed and then you have a retry that would retry that logic. But with this your idempotent key, as soon as you try to do a retry, it checks if that transaction has been marked as paid or completed, and then it prevents the retry. That way it keeps keeps the system accountable and clean of possible errors. Then the design is to store the idempotent keys on the server or the model precisely. It must be deterministic based on retries, and then you might also have to use a signature-based verification to verify that transaction and also prevent replay attack protections too. Then these are another important features where you have to do with the event-driven architecture. So what that means is activities are done based on events. So let's say someone tries to make a transaction, it calls the wallet model, it calls the transaction models first. From there, it calls the wallet model. So more like they are based on triggers. So you have the audit service, the fraud engine that detects anomaly notifications to trigger notifications based on actions. If someone does a top up, you notify the person, or maybe someone signed up, you can notify the person of those activities. And we have the reconciliation processor that tends to ensure that there's no conflict of figures when you are reconciling the activity. So what this helps is it helps to ensure the coupling. It helps to ensure that you're able to replay activities and know exactly where something went wrong or where it didn't go as expected. It ensures you're able to scale your system easily. Then also observability, you're able to view what happened at what instance, and then you're able to isolate issues and faults without having to affect other services in question. So this is more like the failure modes. The major failure causes experience in fintech space. You have the double charge, and the reason why we usually have double charge is when you have a retry raise. More like the transaction failed the first time. Maybe you queued it on Redis or on any queuing caching infrastructure, and then maybe for some reasons it still makes that retry multiple times, and you don't have the idempotent key. With that, it's going to cause refund liability. But with the key, you're able to know that okay, this operation has already run before, and then you prevent the retry from running again. And you have ledger mismatch, and the usual cause is when you have TRX that are not atomic. More like, for instance, someone is trying to fund the wallet, and instead of you actually committing that in a transaction, because you have to create a transaction, you have to update the wallet. So if you don't put that in a transaction, for some reasons, it fails after it creates its transaction. That will create inconsistent accounting, and then that transaction becomes non-atomic. Another one is callback proof. And this callback proof happens most often at times. Let's say you have an external system where you are integrating a payment system, and for some reasons, you actually do not use an HMAC verification to be able to verify the signature and verify the data you are receiving. And you are from there, people attack you or send invalid data that are not actually correct. So the key to that is to ensure that you have an HMAC that is working in reality. Then account balance sync. This is more often when the user's account balance does not tally with what the ledger is saying. So like we've been iterating so far, you have to consider your ledger first to be able to get the actual and final balance of a particular wallet. Then we have the secure authentication and authorization architecture. So we employ beyond the normal JWT, that's JSON Web Token security. You also have to ensure you have the role-based access control, where you make the tokens short-lived based on duration, and they don't span for a long time. And you also ensure that you assign roles based on the least privilege principle. So you don't give roles to users unless they need that role. So you give the minimum possible role to the user. That way, it cops the activities in case the user is compromised. So that means when they're compromised, they have limited access to various functions. Then service-to-service security, you should ensure you use key management strategy when interfacing with external APIs or services. You should ensure you also encrypt your data in communication and also ensure valid and strong authentication. Scalability and production readiness. So in order to be certain that your system is scalable, you have to employ these metrics in the sense that your APIs must be stateless and immutable and immune to obstruction and downtime. You should ensure that you can scale horizontally while also being able to scale vertically. That means you can actually add more CPU or more hardwares while also being able to add vertical scaling if necessary. You should ensure load balancing. That means you should be able to control your traffic. You should be able to manage your infrastructures, and most of the time you have to use infrastructure such as Kubernetes, or you use Docker Kubernetes to ensure that you have good load balancing and your app is readily available at any point. The message queuing too. If for instance you are doing a broadcast, you don't want to execute that instantly because that will add more load to your system. So what that means is you want to queue those loads so that they don't have impact on the system in full force. And then you have read replicas. That means, for instance, if you are using MongoDB database, you can have replicas in different areas so that the database is accessible easily, and also you share the load across those databases and improve efficiency. Then you cache as performance, not authority. So what that means is you should cache instances where they make queries often, so as to prevent direct access to database and also reduce costs while improving your efficiency. Then you should degrade gracefully. So when you actually have to degrade, it should not be impactful that your users start feeling some instabilities on the application. So this is like a diagram of a comprehensive architecture of what a fintech system should look like. So this is a microservice architecture where we have the event bus. In this case scenario, is Kafka. It could be, we have different kind of event bus, but in this case, we have Kafka that manages the events. So when, for instance, for every activity is being made, this keeps tracks of them and emits to the right service. So here we have the auth service, user service, transaction service, the wallet service, fraud service. This fraud determines, checks for anomalies in the transaction and flags them based on the metric set. And you have the gateway that interfaces with the clients. You have the load balancer. For every request that comes, the load balancer determines which of the loads which of the traffic or location or CDN it should direct that traffic to. And we have the DOS attack. You prevent your systems from DOS attack. That's, for instance, someone tried to use a bot to DDoS your system, more like consistent access of particular endpoint. Ensure that your system is immune to that. And you should ensure you use KMS. That's, you should use probably, we have Amazon key management system that helps to keep your sensitive keys for security's sake. Then you have the Redis cluster. So this is the cache layer we talked about. You have to add this in between your users, services, and database so that not all activities will go to your database and help improve your latency and increase your query time to reduce your query time for efficiency. Then this is the part we talked about, database replicas, where you are able to actually have replicas so as to be able to share the workforce among the different requests and queries that come into your database. Then this is more like objects. In this case, you could use S3, you could use S3 or other infrastructures. Yeah, for here you have to have reporting system that keeps track of your reporting on the system and be able to communicate and ensure that you're able to retrace whatever events that happens on the system. Then CI/CD deployment, that means for easy deployment, you don't have to, more like as soon as you commit or push to a branch, your test cases run, and then when those test cases pass, it automatically deploys to production, because you should have your staging instance and production instance to manage the different diversions and features and releases. Yeah, and then the Kubernetes I mentioned earlier. So this is more like being able to auto scale based on your traffic. Your system is able to contrast and expand based on the current traffic on the system. Then fraud and abuse prevention. We saw that earlier. So you should have system in place beyond your rate limiting. You should also have system in place that would help detect anomaly. For instance, someone logged in from a certain location, and then we are having varying pattern in a particular user's transaction. That should also be flagged. We have velocity checks. So the velocity check is more like maybe someone makes 500 transactions in 1 minute. That's suspicious. So you should be able to detect that this is actually not normal, or maybe someone moves like huge amount, like £5,000 or thereabouts within 1 day. Like those kind of unusual activities are things that your velocity check should be able to flag and prevent that. Then beyond using the user's fingerprint, it should also keep track of the user's device ID or model. All those also help prevent unusual activity. Then risk scoring models and set up strong authentications like OTP. Maybe someone wants to make a transaction, you have to request for an extra layer of OTP authentication or mnemonics, security mnemonics. The fintech industry is also faced with regulations and compliances that needs to be done. These are like PCI DSS as the card compliance principles, GDPR, your data compliance, also encryption at rest. So you want to also ensure that users' data are safe both in rest and in transit. So let's say, for instance, someone is trying to make wallet transaction, you want to encrypt at the client side, and then it passes through the HTTP communication parts to the backend, and backend you decrypt again and get relevant information, and your keys are actually known and isolated from the transaction. Then access login should be able to they should be able to log all the activities for audit purposes, data retention policies based on how long you want to hold users' data when they decide not to continue with your service. Then this is more like you should be able to retrace the activities and make a forensic analysis of a transaction. And the major failures are usually due to auth bug. Maybe a user was not fully validated and makes a transaction that is not expected, or due to retry and you don't have an idempotent key, and then you have retries that duplicate transactions, and this is ledger bug. More like you don't actually verify from the ledger before implementing or incrementing or decrementing a user's balance, and most often those create bugs and issues for fintech industries. So the keynote is that money must move atomically. That means it's either you move all or you don't move anything. Is that the whole transaction goes through, or you stop everything? That means is that is 1 or is 0? It cannot be 1 point or in between. So never trust balances, but trust ledgers as source of truth. And that thing you could do is to, I mentioned that earlier, when you change your transactions, that way it's also immune against manipulation or alterations that are not authorized. So you design for failure even before they happen. That means your architecture should actually factor in failures, factor in negative scenarios to be able to build it and fortify the architecture. Adaptability is not optional. Yeah, because you have to be able to know what is happening in your system at any point in time. So it's important the system gets logs. Yeah, and that's that. Thank you for your time. I hope you got the whole message. Thank you. Any question from my end?